one more piece of kinetic information, because I've told you about GLUT2. We learned about GLUT2 in enterocytes. We learned about GLUT2 on beta cells. And now we've learned about GLUT4. What are all these glucose molecules for? Well, let's talk kinetics. After all, this is biochemistry, right? I heard the sigh. That's perfectly okay. Sigh all you want. I think it was last year, one of the students in last year's class, I remember going into one of these pathways and I got the kinetics and I heard somebody in the back go, "Oh, good God." This means I'm doing my job, right? Okay, so if I show you the kinetics, so we're going to measure glucose transport of a transporter. We're going to measure that by glucose concentration. So remember your basic kinetics. When you have a saturable process, that typically means you got a protein involved. So if I show you kinetics like this, what this indicates is that as you increase the concentration of glucose, the amount of glucose transport by that transported by that transporter is going to increase. But it's only going to increase to a certain point because you've saturated the transporter. So if you have, let's say you have 100 molecules of transporter. Down here, if you have 10 molecules of glucose transported, you're not going to be saturating because you got 100 molecules to transport the 10. But now let's say out to here you've got 10,000 molecules of glucose and still only 100 molecules of transporter. That's as fast as that transporter can go because you've saturated them all. So this, remember what that's called?
Vmax.
Ooh, nice. That's Vmax. It's the maximum velocity that these transporters can transport anything. Transporters can transport. So what if I told you this was GLUT4? This is our high affinity. Transporter. What's that? No pressure, since you said Vmax before. 1/2 Vmax. And then this is Km. Good. Now why am I dragging you through this? Because these type of questions are on step 1. Guaranteed. Yeah, you have to know kinetics. Again, really? Okay, so Km. So this Km defines GLUT4. Now, what if I was to show you this? Look what we've done to the Km. Let's say they have the let's say they pretty much have the same Vmax. They can transport glucose at the same rate when you've got enormous glucose concentrations. GLUT4 is on skeletal muscle because when you have in a fed state, you want skeletal muscle to have glucose available because this in skeletal muscle needs to recharge ATP and it needs to store glucose as glycogen for when you go into a fasting state. So logically, you want a high affinity, low Km transporter. You want to pull that glucose in as fast as you possibly can. What about GLUT2? Now GLUT2 is considered a low affinity transporter, and this is on beta cells. Now remember the function of beta cells. This is sensing glucose in a fed state. The purpose of the beta cell is to sense elevated glucose concentrations, not glucose concentrations when you're at fasting levels. So when you're at fasting levels, you want to shut off insulin signaling. So the way the body does this is by altering where it puts these glucose transporters. So GLUT2 is only going to work when you have high concentrations of glucose. So let's say that this is the fed glucose concentration. Let's say this is fasting here. So when we consume our glucose, our fed concentration, our concentration of glucose goes up, and look at the activity of the GLUT2 transporter. It's very active. Very active because you want your sensing beta cells to be actively taking up glucose to induce the signals for insulin secretion. As the skeletal muscle is responding by going out to the surface to the insulin signaling, it's starting to decrease the concentration of glucose in the plasma. And again, this is primarily due to skeletal muscle activity and GLUT4. Because look at the affinity of GLUT4. It's extremely high in the fed state, and it's also very high in the fasting state. So in the fed state, let's take advantage of that. In the fasting state, let's pull that GLUT4 back inside cells so that we don't drop our glucose levels. Now in the beta cell, we want the beta cell to have lots of activity in the fed state for insulin secretion. But then when we get down to the fasting state, we want to decrease that activity of the beta cells. And it's simply done by not changing GLUT2 activity, but changing its affinity, by taking advantage of the affinity difference in GLUT2. So with lower plasma glucose concentrations, the activity of GLUT2 drops. And what this means is a decrease in insulin secretion. Now, remember I said in that insulin never goes away. Even in the fasting state, you can still measure insulin. And that's because you still have some residual GLUT2 activity in the normal fasting state. And it has all to do with this kinetic curve. Now, brain. Good example. Brain uses glucose all the time. We need glucose oxidation in the brain. So knowing this kinetic difference, would you rather have a high affinity or low affinity transporter on your neurons? High affinity. Because it doesn't matter what your glucose levels are in your blood. Your brain needs to get at that glucose. And so let's put GLUT3 up here. So the affinity for glucose, for GLUT3 and GLUT4 are similar. They're both very high affinity. The other glucose transporter is GLUT1. GLUT1 is found predominantly on red blood cells. Do you want red blood cells to be able to have access to glucose at any concentration? Why?
Is there only one production making ATP?
It's the only way they can make ATP. They have no mitochondria. They don't have mitochondria because you don't want your red blood cells doing aerobic respiration because they got oxygen for everybody else. So you want to make sure that you have a high concentration of glucose available to them. So let's do this. Now what about the liver? Liver's metabolically active. Think about the liver as being altruistic. The purpose of the liver is to take care of all the organs in the body. So it's going to take glucose and it's going to make fat out of glucose to store it for extra energy for the body at a later time. It's going to take glucose and store it as glycogen, not for itself, but to put it back out into the circulation during fasting state to keep your blood glucose levels up during fasting, keep you from going hypoglycemic. So if the liver's job is to make sure that glucose is available for all the cells of the body except itself, would you think the liver would have a high affinity transporter or a low affinity transporter? Low affinity. So GLUT2 is on beta cells plus hepatocytes. Now the liver has a low affinity transporter because it's only going to take glucose from its other organs when you're in a fed state, when there's abundant extra glucose present in the blood. As you go into a fasting state, the liver is going to be taking less glucose out of the circulation because it knows the brain needs it. It knows the red blood cells need it. It knows the kidney needs it. And so GLUT2, for that reason, is present on hepatocytes. Yes?
In the drawing that you have for GLUT2, it seems like the Vmax doesn't reach the same level of Vmax as
Yeah, it's actually lower. It's actually lower. The key on the graph, on the picture here, and what I've drawn is just remember the affinity. High affinity versus low affinity, and the reason why the cell type has that type. Okay? So the other important thing that's always comes up as a test question is, of the glucose transporters, which ones are insulin responsive? Would you want GLUT3 on your neurons to be insulin responsive? Nope. You don't want access to glucose for your brain only when you eat. You want it all the time. How about red blood cells? All the time access. So these transporters, GLUT1 and GLUT3, are on the surface all the time, as is GLUT2. GLUT4 is the only one that is insulin responsive.